गएको लेक्चरमा वी वर टकिङ अबाउट दि एक्टिभेटेड स्लज प्रोसेसको बारेमा हामी कुरा गर्दै थियौँ र हामीले केही इक्वेसन्सहरू हेऱ्यौँ र हाउ दे क्यान बी डिटर्माइन्ड है इन टर्म्स अफ एक्टिभेटेड स्लजको प्रोसेसमा हामीले सबस्ट्रेट र हामीले के गर्यौँ त सबस्ट्रेट र त्यसको बायोमासको मास ब्यालेन्सबाट we saw that there we derived some equations, right? I think we talked about, let me go over to the equations. So we derived some equations using the substrate as well as the biomass को चाहिँ ब्याक्टेरिया अथवा बायोमासको ब्यालेन्सबाट we determine some डिजाइन इक्वेसन्स है। त्यसै गरी हामीले स्लज प्रोडक्सनको इक्वेसन हेऱ्यौँ। एफ्लुएन्टमा चाहिँ बिओडी भनेको बायोडिग्रेडेबल सिओडीको होइन। सो नर्मली तपाईँको चाहिँ बायोडिग्रेडेबल सिओडी र उसको रिलेसनसिप चाहिँ बायोडिग्रेडेबल सिओडी र बिओडीको रिलेसनसिप चाहिँ अराउन्ड 1.6 टाइम बिओडी हुन्छ होइन। सो जेनरली तपाईँको बायोडिग्रेडेबल सिओडी भनेको चाहिँ इट्स अलमोस्ट 1.6 टाइम अफ बायोलोजिकल अक्सिजन डिमान्ड। त्यसै गरी सबस्ट्रेट स्पेसिफिक सबस्ट्रेट युटिलाइजेसन रेटको कुराहरू पनि हेऱ्यौँ हामीले होइन। त्यसै गरी फुड टु बायो माइक्रो अर्गानिजम्स रेसियो को चाहिँ एउटा डिजाइन इक्वेसन्सको कुराहरू हेऱ्यौँ। सो I think while doing that, so let me slightly revise what we have covered in our last lecture. So I think in the last lecture, so we talked about the activated sludge process. So normally what activated sludge process is actually a biological system that consists of a suspended growth microorganism. त्यसको लागि what we need is you need a aeration tank and then you need a solid liquid separation process होइन। भनेको सेकेन्डरी क्ल्यारिफायर तपाईँलाई चाहिन्छ हुन त सबै एक्टिभेटेड स्लज प्रोसेसमा यु मे नट निड अ सोलिड लिक्विड सेपरेसन प्रोसेस। लेट्स से एरिएटेड लगुन होइन। एरिएटेड lagoons is also activated sludge process where you do not normally we do not apply the secondary clarifier for the aerated lagoons. So mainly this is used for compact type of a compact type of activated sludge like the extended aeration, CMS, conventional activated sludge processमा मात्र हामीले solid liquid separation चाहिँ use गर्छौँ। So there are three things are required होइन। So you need an aeration tank, you need a aeration tank to grow the microorganism, you need a solid liquid separation process, or maybe sometimes if it's a recycle process you need a recirculation line. So three things are required for the activated sludge process. तपाईँको इन्फ्लुएन्टमा what we in the influent wastewater you have around 220 milligrams of TSS, while inside the aeration tank we have 1500 to 4000 milligram of MLSS or close to 2000 milligram of MLBSS. So this is how activated sludge configuration looks like. So this entire wastewater supply chain train, wastewater treatment train, sorry. So you can see here the screen is there, aerated or some non-aerated grid chamber is there is a primary clarifier there. So this is a preliminary treatment. So these are preliminary treatment. So we already talked about the preliminary and the primary treatment in water quality engineering. So primary treatment. So afterwards there is a aeration tank. So where there is this is a biological system. So this is consisting of activated sludge process where there is a solid liquid separation process, aeration tank, return activated sludge, the waste activated sludge is there. So this is it. So and then we looked into the problem of a system activated sludge system without sludge recycle and a system with sludge recycle. Right? So even in a system with sludge recycle, we discussed the two options. So one from underflow of the settling tank. So if you are still remembering the lecture from our water quality engineering, so we did some flow, like we talked about some flux theory or type 3 as well as type 4 sedimentation. So for designing a settling tank. So settling secondary clarifier, the design of secondary clarifier, it's entirely a different. It follows a different approach. So I think we will also talk about this in the setting. I think it's in the there's a separate chapter for that. ओके सो अब यसलाई चाहिँ तपाईँको हामीले वेस्टेज दुई तरिकाले गर्न सक्यो एउटा चाहिँ डाइरेक्टली फ्रम द एरिएसन ट्याङ्क ओ मेबी फ्रम द एफ्लुएन्ट अफ द एरिएसन ट्याङ्क ओ मेबी आफ्टर दि सेटलिङ ट्याङ्क होइन सो देयर अब तपाईँको एरिएसन ट्याङ्कबाट डाइरेक्टली इफ यु आर wasting it, then the concentration of the microorganism or biomass in the waste activated sludge is same as in the aeration tank. While if you are wasting the sludge from the settling tank, then the concentration is quite high. So it's a very thick concentration. So अब यो concentration कसरी हामीले determine गर्ने त? I think this is important to know because I think we also define the SRT as the mass of solids in the reactor, mass of solids in reactor divided by mass of solids leaving the system. Solids leaving the system. So if you want to calculate the SRT for, let's say, for this kind of system and this kind of system, you need a ratio between mass of solids inside the aeration tank and mass of solids leaving from the system. So normally what we do is while calculating the SRT, we consider that there is negligible losses in the effluent. So only the losses is via the waste activated sludge. So this is the assumption we make. While in the sludge without recirculation, so we what in this system, so your HRT or hydraulic retention time is the same as the SRT. While in the system with recirculation, your SRT is much more larger or it's a longer than the HRT. So okay, so let's look at the sum of the system. Within the activated sludge treatment process, so it can be a high rate system where the food to microorganism ratio that is measured as the total BOD coming into the reactor. So the concentration of the BOD in the effluent or the coming in, that is into the reactor multiplied by the biomass into the system. So biomass and the multiplied concentration multiplied by the working product. So this gives you the food to microorganism ratio in the system, right? Okay, so for the extended aeration process, so so it means that the obviously the SRT is long because it extended aeration. So in this system, so normally what happens is we keep the very long SRT. So this means that there is enough time for the sludge to stay in the reactor. So your system ma ke huncha ta extended aeration, there is a chance that the microorganisms or the biomass is stabilized compared with the conventional system. So also the loading rate or the food to microorganism ratio is also less in the extended aeration compared with the high rate. In a high rate process, both your OLR is quite high and your HRT is quite small, right, compared with the extended aeration. While in the conventional activated sludge process, we keep it between the 0.8 to so 2 2 kg per kg MLSS per day. So that is the food to microorganism ratio. Also, there are several systems. So within the activated sludge process, so depending on the operational parameters like the food to microorganism ratio, to how long is your SRT, how long is your HRT, and your food to microorganism ratio or your recirculation ratio. So you have a different kinds of system, right? Basically, the biomass concentration in the reactor is also it's quite different, right? So you can see that in the conventional aeration, conventional activated sludge process, or completely mixed system or step aeration process, you have a different kinds of the operating parameters are there. So also it is a pure oxygen process. So normally this is quite well. There are these process where they use a pure. You can use a pure oxygen, but and then the process efficiency is also high. The loading rate you can check is quite high, you know, because the yield would be quite high. And also the biomass concentration you can maintain in the reactor is quite high. So depending on so which type of operational process operational parameter you like to keep. So let's say if someone wants to have their sludge slightly stabilized or maybe somewhat stabilized and they don't want to have a sludge treatment. So let's say they want to dewater their sludge, and also they want some sort of nutrient removal. Then maybe someone would like to go for extended aeration. So an example is kind of a oxidation ditch. So oxidation ditch is an example, right? So where you have a longer SRT, and then, and let's say, and then in the generally in the conventional or a completely mixed system, you have a shorter HRT, but depending on whether you would like to have a nitrification or not, so you can select the proper SRT, right? So SRT को कुरा पनि हामीले गर्यौं. So SRT mathematically it means the mass of solids in the reactor divided by mass of solids leaving from the reactor. But principally how we control the SRT, एसआरटीलाई हामीले कसरी कन्ट्रोल गर्छौँ भने, एसआरटीलाई आई थिङ्क we also express the SRT as um, I think we express the SRT as SRT लाई हामीले derive गर्दाखेरि, so it volume of the reactor, working volume of the reactor divided by sludge को चाहिँ वेस्टेज को फ्लो, वेस्टेज को चाहिँ फ्लो रेट, हैन. सो हामीले के पनि भनेको थियौँ त एसआरटीलाई. So we can control the SRT by controlling the wastage को flow. So let's say if you keep if you are like daily you are wasting, let's say 1/10 of the volume of the working volume of the reactor, then you can keep the SRT as 10 days भनेर हामीले भने हैन. So let's say if you are wasting 1/10 of the reactor volume, then right, you can the SRT is around कति त. So your SRT, let's say if you are wasting uh, let's say 1/10 of the volume in a day, uh, then your SRT will be around 10 days, right? So also depending on the different kinds of aeration system, let's say for different systems, let's say the conventional system, extended aeration system, there are some different recommended aeration systems are there, as well as the BOD. And the outcome of the BOD removal efficiency is also can be predicted. And so let's say for the most often the plug flow configuration, say to make a conventional system, let's say if you have oxidation ditch kind of process, optimum operate गर्नुभयो भने, so what happens in the oxidation ditch is you have a aeration tank at the two ends of the tank, right? So there are several. So it's a kind of a plug flow configuration, right? So there is a several zones are created. So this is a aeration zone, maybe the anaerobic zone somewhere in between, anoxic zone. Different zones are there. So in this case, maybe you can apply the mechanical. So there is no need of diffuse aeration system, because diffuse aeration system is it facilitates the proper mixing. So हामीले गोइसोरीमा last time भिजिटमा जाँदा जुन system, that's a kind of diffuse aeration system where they have used a diffuse aerators like the fine bubble aerators, right? Or medium bubble aerators use. So while in the surface aerators are the systems, they have a low so oxygen तपाईँको चाहिँ low, they have low aeration efficiency, होइन. surface यो aeration efficiency चाहिँ या transfer efficiency चाहिँ एकदम कम हुन्छ compared with the diffuse aeration system. So and then the given like the expected removal efficiency percentage is also different. So it's up to the designer's discretion. So what kind of system they would like to design. Also it depends on the purpose, तपाईँको वेस्ट प्रडक्टको characteristics, also the purpose of the treatment plan, त्यसरी तपाईँले अघि मैले भने जस्तो if you want to have somewhat stabilized sludge without any sludge treatment, then maybe you would like to apply either extended aeration or maybe a conventional system with a very long SRT. So where you can achieve a nitrification or some sort of nutrient removal as well, right? So basically, if you want to maybe let's say have a efficient kind of aeration, then maybe the step aeration. So or step feeding kind of system is there. So so instead of influent feeding this way, you feed the influent in the so step feed cargo systems are there. So हामीले जुन गोइसोरीमा देख्यौँ त्यो सिस्टममा के थियो त, so influent are fed from this side while the aeration is decreased. So because at the this section of the reactor you need to remove let's say your oxygen, carbonaceous oxygen demand is more in this part compared with this So you decrease the aeration in this way, right? So so the different operational strategies are there. So depending on the different kinds of activated slots technology or the process you would like to apply, so you can select the different system. Okay. Um, okay, so these are the kinds of the mechanical or the surface radiators, right? So they are like fixed to some motor, right? And has a surface aeration. So depending on the कति depth चाहिँ you insert it, also the aeration efficiencies are affected, right? So aeration efficiency. While in the diffuse system के हुन्छ त तपाईँको चाहिँ the air is diffused from the होइन either from the coarse bubble or fine bubble diffusers, right? So so within the activated sludge process you can operate a different technology. So different technology they have different objective, होइन जस्तै तपाईँको high rate processes is normally used to take up the high organic loading rate, while the extended aeration processes are more maybe low cost settingमा स्लजको चाहिँ ट्रिटमेन्ट रिक्वायरमेन्ट्सलाई घटाउनको लागि होइन त्यसरी पनि युज गर्ने हुन्छ. While there are both advantages and disadvantages, so we'll come to that later on. So in the extended aeration process, your carbonaceous oxygen demand is much more higher than in the your conventional process, है. So त्यसै गरी तपाईँको स्लजको चाहिँ स्ट्याबलाइजेसन बढी हुन्छ. While in the conventional high rate you have a higher maybe the higher sludge production, होइन फ्रेस स्लजबाट त्यस्तो खालको स्लजबाट you can generate the biogas in the anaerobic digestion process. So that is the sludge production plant. So okay, so again we slightly talked about the return activated sludge or the so you let's draw on one diagram again. So you have an aeration tank, you have a secondary clarifier, uh, and then let's say there is a sludge wastage from the secondary clarifier, and then there is a recirculation. Sorry, we call a recirculation as a return activated sludge. So there is a recirculation system. So let's say this is a secondary clarifier. So अब यहाँ जुन यो बायोमासको जुन कन्सन्ट्रेसन छ यहाँ यो जुन वेस्टेज लाइनमा अथवा भनौँ यो रिसर्कुलेसन लाइनमा. So how to predict if you let's say if you wastage from here, if you do not waste from here, then the concentration in the waste activated sludge is the same as the x. So reactoरमा x concentration biomass छ भने वेस्टेजमा पनि x. But if you are settling using some solid liquid separation process and wasting it from the underneath or underflow of the solid liquid separation process, then you can predict the concentration of the biomass in the wastage or in the return activated sludge. You can predict it using a SBI. So SBI is a sludge volume index. So in भनौँ यसलाई यसको inference चाहिँ it is a volume occupied by a 1 gram of sludge, simply भन्दाखेरि. So SBI is a volume occupied by 1 gram of sludge. So that's why its unit is so milligram. How much milligram of volume is occupied by a gram of sludge? So actually, so how we calculate the SBI? So the SBI is calculated using a graduated cylinder. Let's say you take a aeration tank effluent like तपाईँले लिनुहुन्छ. Aeration tank effluent like you take a aeration tank effluent or sample it from the aeration tank, and you take a 1 liter graduated cylinder, and then you keep this sludge in a, let's say, representative sample. You take a representative sample of the activated sludge effluent, and then you keep it in the graduated cylinder for 30 minutes settling. So in a 30-minute settling, so you see the sludge चाहिँ कहाँ गएर सेटल भएको छ त. लेट्स से इन द ग्रेजुएटेड यो सिलिन्डरको लेट्स से 200 मिलिग्राम जति यसले अकुपाई गर्यो, लेट्स से 1 लिटर स्लजले भने then you consider that okay, the sludge settled sludge ko volume in 1 liter is it's 200 milligram per liter. Let's say suspended solids ko concentration aeration tank ma jun sample linu bhacha cha, so what is the MLSS in there, हैन. So MLSS को concentration गरियो. So that is a suspended solids concentration. So you take this value, so the sludge divide, let's consider let's take an example. Let's say the SS or MLSS is it's 2500 milligram per liter. Then and then we can calculate the SBI value here. Let's say after 30 minutes of settling, your 1 liter sludge occupies 200 ml. And then let's say the suspended solids concentration in the or MLSS is around 2500. milligram per liter. So in this case, I think we are using this 1000 to just convert it into gram, milligram into gram. So in this case, your SBI is, so how much is your SBI? So your SBI is around, okay. So SBI concentration is, so how much is it? It's 200 divided by 2500. So your value of your SBI is, so 80, right? So your value of your SBI is, let's say it's 80 ml per gram. So when your sludge SBI is, let's say, less than 100, so you can, what you can infer is that you can infer, sorry, you can infer that the, um, can infer that the sludge is very good set reliability. And sludge को set reliability चाहिँ is good enough. So if your SBI is less than 1, so less the value of SBI, this means that the sludge चाहिँ थोरै होइन, थोरै भन्दा थोरै sludge चाहिँ सेटल हुँदछ. अझ यो 200 मा नभएर 100 मा सेटल भयो भने, so 100 ml 1000 को sludge होइन, अब यहाँ माथि is this the water while the sludge is in the 100 ml. So this means अब यहाँ तपाईँको अझ हेर्नुभयो भने कति हुन्छ, even like this, the value is even less than 80 ml per gram होइन. So if you take, let's say, XR को value अथवा यो return activated sludge मा sludge concentration can be calculated XR equals to 1 by SBI. Let's say if your SBI value is 100 milligram per gram, then your calculated the biomass concentration in your wastage or your return activated sludge is around 10,000 milligram per liters होइन. सो भनौँ तपाईँको रियाक्टरभित्र 2500 थियो भने मेबी इन your return activated sludge, so the value of your concentration or your biomass is XR. Let's say if it's XR is the, so this is around quite high. So in this case it's 10,000. We calculated it as a 10,000 milligram per liter. If your SBI is around 100. So this is also can be used to predict the, actually it can make, it makes some sense because SBI can give an idea about the settleability of the sludge. So you can give an idea. So after settling, so what will be the concentration of the underflow or the waste activated sludge, right? You can predict in using the taking the SBI value. So I think, I don't know if there is any question so far, please feel free to ask. त्यसै गरी यो रिसाइकल or recirculation ratio भनेको इट्स अ रेसियो बिट्विन दि, the ratio between the return activated sludge को flow rate होइन, divided by your flow rate that is coming into the, let's say if the Q is your flow rate coming into the treatment plant, let's say QR is your recirculation flow, then the recirculation ratio, so if you see, then the recirculation ratio is the QR divided by Q. So this will give you the recirculation ratio. So if you see the different system, it's a conventional activated sludge process. The recirculation ratio can vary between like 25 percentage of the inflow of Q to 500 percentage of the total inflow होइन. So depending on the तपाईँको चाहिँ influent characteristics, so your sludge production can be affected, so as your recirculation rate है, recirculation को rate पनि त्यसै गरी affect हुन्छ. So you can see that the different concentration of biomass has been maintained. So you can see that in the modified aeration, it's only 200 to 500 biomass. It's in the step aeration 3000. Conventional activated sludge, completely mixed system around 3000 to 6000. I think when last time we visited the Goeswari activated sludge, I think they have a concentration around 4000 and 500. I think the treatment plant has been designed and operated as a CMS system. The concentration of the biomass there during the visit was MLSS, not MLVSS. So there is a difference है. अब हामीले MLSS र MLVSS भन्यौँ. So there is a difference. So MLVSS represents the biomass को चाहिँ organic fraction while the MLSS it represents the all the organic as well as inert fraction. So this typically is around 0.6 to 0.85 some. This can vary. So when you have a high value of MLVSS to MLSS ratio, this means that you may have high active heterotrophic, ordinary heterotrophic organism. When you have a low value, this means that you have more inert in the system and less active biomass. You know? So that is not so good for the operation of the system. And then just to summarize some of the terminologies and the parameters that we use, so के हुन्छ त एक्टिभेट स्लज सिस्टममा भने typically so we call like MLSS, MLVSS. So MLSS it includes the MLVSS plus fixed solids, fixed inert solids. I think this is what we inferred last time. While the MLVSS it represents active biomass, ordinary heterotrophic organism प्लस इन्डोजिनस डिके भएको ब्याक्टेरियाको बायोमास प्लस नन बायोडिग्रेडेबल होइन अरू सस्पेन्डेड सोलिड्स मे बी इन्क्लुड बट द्याट आर अर्ग्यानिक होइन द्याट आर अर्ग्यानिक सोलिड्स चाहिँ एमएलएसएस त्यसै गरी आई थिङ्क इन एडिसन टु द इक्वेसन वी स before we also we try to limit the number of kinetic parameters and derive this simple equation. I think for both system with recirculation and system without recirculation. So 1 by theta c is your let's say the design minimum SRT can be calculated using the yield put to microorganism ratio and the desired efficiency as well as the decay coefficient. So that can be is represented KD or B. Right? So okay. So what happens is when you have a high FM ratio, when you have a high FM ratio, the flux doesn't settle. So during the high FM ratio, it can be possible that you have a more filamentous bacteria growth चाहिँ बढी फेसिलिटेट हुनसक्छ. फिलामेन्टस ब्याक्टेरिया को ग्रोथ भयो भने के हुन्छ त when you have a filamentous bacteria, this means that the sludge is bulking हुन थाल्छ sludge को है sludge is so यसको राम्रोसँग सेटलमेन्ट अघि हामीले एसबीआई को कुरा गर्यौं. So the sludge with the filamentous bacteria they don't have a good SBI values, they have very higher SBI values. So typically this is also we would like to limit. So त्यसै गरी अब low FM ratio मा के हुन्छ त flux can settle properly but also the treatment efficiency is high. So we will try to find a balance. अब low FM ratio apply गर्यो भने हाम्रो OLR को value कम भयो. This means that you can have some organic loading rate as well as hydraulic loading को चाहिँ limitation हुन सक्छ. So there is a optimization is necessary. Okay. I think another thing is I think we talked about MLSS and then the FM ratio. Okay, so FM ratio also affects the if so filamentous bacteria grows then the bulking occurs. So bulking चाहिँ अब के हुन्छ त तपाईको secondary clarifier मा normally the after the aeration tank and the secondary clarifier you have a effluent. So effluent मा अब के हुन्छ TSS बढी भयो नि so it does not give a very good signal that it means that the treatment plants are not doing good. अब त्यसको पनि तपाईको लिमिटेसन हुन्छ टिपिकली 50 to 60 चाहिँ मिलिग्राम पर लिटर को चाहिँ तपाईको TSS को लिमिटेसन हुन्छ इन द एफ्लुएन्ट. So when you have a sludge bulking then you cannot maybe meet these effluent को चाहिँ treatment recommendation चाहिँ meet गर्न सके. I think we also talked about the return sludge ratio, recirculation ratio as well as the nominal as well as the actual hydraulic retention time, mean solid retention time MCRT or MCRT or SRT or हामीले के भन्यो भने like theta c we define it in or sludge age or we also call it sludge age. Sludge age भन्यौं. So yes के हुँदो रहेछ त so it means that the solids within the inside the reactor divided by the solids leaving the system. So normally by controlling the SRT you can control the growth of the nitrifiers. So normally nitrifiers भनेको के त so nitrifiers are those microorganisms who can convert the ammonia into the nitrate. So if you want nitrification in the system so you want to have like more SRT. त्यसै गरी winter time मा you want to increase your SRT during the winter because in the winter time you have the growth is compromised the velocity of the growth is compromised. So त्यसै गरी अघि हामीले भोलोमेट्रिक लोडिङ रेटको कुरा गऱ्यौँ। त्यसै गरी वी अल्सो टक्ड अबाउट दि आई थिङ्क वी अल्सो टक्ड अबाउट दि हाइड्रोलिक लोडिङ रेट. सो नर्मली भोलोमेट्रिक लोडिङ रेट भनेको चाहिँ के हो त, पर मिटर क्युब अफ द रियाक्टर हाउ मेनी केजी अफ बिओडी you load per day. So this is the organic loading rate. So hydraulic loading rate is the how much, let's say, volumetric hydraulic loading rate is the meter cube of the reactor per meter cube of the reactor per day. Or maybe कतिपय केसमा सर्फेस लोडिङ रेट भन्यो भने मिटर क्युब अफ द वेस्ट वाटर पर मिटर स्क्वायर अफ द रियाक्टर पर डे भनेर पनि हामीले वी क्यान क्लासिफाई. एन्ड अल्सो वी आई थिङ्क अलरेडी टक्ड अबाउट दि स्लज भोल्युम इन्डेक्स एन्ड इट्स सिग्निफिकेन्स होइन. सो कहिलेकाहीँ कस्तो हुन्छ त भने एक्टिभेटेड स्लज प्रोसेसको चाहिँ अपरेसनको बेलामा ड्युरिङ इट्स अपरेसन दि स्टार्टअप भनौँ न, अपरेसन भन्दा ड्युरिङ द स्टार्टअप. सो यु हेभ दिस काइन्ड अफ प्रब्लम. सो यु हेभ अ forming problem. So this is an indication that this is a high O2 uptake rate is there. So this picture is the initial operating period of wastewater treatment plant. So this is the old aeration tank. This is the old aeration tank. I think we didn't visit there. So we only visited the new aeration tank, which is on the other side of the. So this is the new aeration, old aeration tank. You can see that forming problem due to the very young sludge, and then the very high FM ratio, and it causes the this kind of. So what we want is we want to have a balance between the old and the young sludge, होइन. So old sludge को very problem के हुन्छ त, old sludge भने के हो त, what does old sludge means is you have a let's say the very high SRT is very high, and then so during the startup period, so we cannot have a, so either you need to bring the sludge from the other treatment plant, otherwise old sludge I think you can maintain. So decreased food intake is there, as well as the low cell production. So the oxidation of the stored food, होइन. So तिनीहरूको आफ्नै इन्डोजिनस चाहिँ डिके तपाईँको हुनसक्छ, जसले गर्दा it can take up the some of the oxygen. So oxygen को demand also increase गरिदिन्छ यसले. So that is not good for the erection energy. Low त्यसै गरी high MLSS is there, high retention time is there. I think also we talked about, I think in the PDF given, I think also there is the oxygen required calculate गरेको छ. I think we also discussed it while I think going through the PDF. त्यसै गरी हामीले oxygen uptake rate को चाहिँ I think we haven't talked. So oxygen uptake rate is actually it's a how much oxygen is required per unit volume of the aeration tank. So that is the oxygen. So RO2 can be calculated using this equation. So divided by the working volume of the reactor. So using this formula, so we can calculate is the oxygen uptake rate. So oxygen uptake rate. They said P. What is P? P is your is the sludge production. P is your sludge production. So you multiply the yield by the how much of BOD is removed, divided by the 1 plus AD theta C. So that is the SRT. So with this you can calculate the sludge production, that is converting the organic. So either the soluble COD, biodegradable soluble COD, अथवा biodegradable particulate COD. So that is biodegradable particulate COD चाहिँ कति छ, यो कति कन्भर्ट हुन्छ त into the bacteria. So this can be calculated using the equation here, होइन. So I think so I will not go through the this aeration, because I think there's I think chapter 6 deals with the different kinds of aeration, and then we'll talk about it in detail. But just to give you some idea in the activated sludge treatment process, so we can use the different kinds of aeration system. So don't worry about this. I'm going to repeat it because there is a separate aeration and the settling. I think chapter is their secondary clarifier. So fine bubble diffusers, they have a very high oxygen transfer, or the air transfer efficiency is there. There's jet aerators, static aerators, and mechanical aerators, which are the surface aerators. So this is the mechanical aerators. So this is the fine bubble aerators. I don't know if I have kept the jet aerator system is not there, but okay. So this is a fine bubble aeration system. So they have a name fine bubble. So it releases very small bubble. So this increases the probability of high probability of transferring the oxygen from the liquid, from the gaseous phase into the liquid phase. That's why they have very high. So per kilowatt of electricity, they can like transfer 3 to 4 kg of oxygen, right? So this is the beauty of the system. While the coarse bubble diffusers, they have slightly lower aeration transfer efficiency, but they are better than the surface radiators, so which have the lower oxygen transfer efficiency. You can see that the fine bubble, they have 3 to 4 kg in clean water, while 2 to 3 kg in the activated sludge system. So while in the surface aerators, they have a per kilowatt hour say energy input दिनुभयो भने चाहिँ 1.82 होइन, त्यो 2.2 चाहिँ ट्रान्सफर गर्छ अहिले होइन. So oxygen can be transferred. So they have different kinds of oxygen transfer efficiencies. You can see these are kind of a jet or यस्तो खालको डिफ्युज सिस्टम नगरिकन, so it can be used, these are oxygen diffusers, so it can be also diffuse aeration can be also done by making a holes in the this kind of structure. Actually this is a MBBR tank. This is a moving bed biofilm reactor tank, but you can see that there is a different aeration grids are there, right? Okay, so this is one completely mixed system go saying, this is a drawing schematic diagram. You can see that the typical values of the SRT FM ratio. So while the operational conditions are given here, and for the completely mixed system. So while in the conventional plug flow system, so what happens is it's a very typical oxidation ditch system. It operates as a plug flow system. So what happens here is you have the high biomass concentration as well as the SRT value is less. And here you can see here that is अब यहाँ चाहिँ के हुन्छ त तपाईँको maybe this zone has a it's a plug flow configuration. Yeah, it's not a CMS system. So you can see that there are several, maybe could be aerobic zones could be there. Also the retention time is it varies between half a day to 2 days for a high rate system, right? So this is a high rate system, so you have a very high FM ratio is high, and the SRT or the SRT is also very low. So while in the conventional system you have 3 to 15 days of SRT 0.2 to 0.4 kg, so the FM ratio is quite low. And so while the extended aeration system, this kind of system, you have very long SRT. So that's why it's because of this. You can also maybe sometimes this system, depending on your feeding regime or the aerobic conditions, I mean where you are feeding your system, so you can also achieve a nitrogen or ammonia removal, like phosphorus removal can be achieved in the extended aeration system. So you have a very low FM ratio while very high SRT, right? So again, so this is you can see that the carousel type of oxidation ditch system is this. So I think earlier the Goesori, I think the photo I have shared. Let me go back again. Okay. So actually, this system used to be a carousel type oxidation ditch. Okay, so यहाँ के थियो त पहिला भन्दाखेरि, so in the other end there was a one aeration system, and this end there was one aeration system. So when wastewater moves this direction, के हुन्थ्यो त यहाँ एरिएसन सिस्टम यतिमा एरिएसन हुन्थ्यो, and then somewhere there is a different anoxic zones are there, फेरि यहाँ एरिएट हुन्थ्यो होइन, and then there is a the outlet. So this kind of system was there. So this is a very classic example of carousel type of oxidation ditch. Right? So this is another kind of a plug flow extended aeration system. Right? I think we talked about the so obviously aeration ASP को design चाहिँ so केमा govern गर्छ त, it depends on what is the design effluent BOD level. Right? So what would be the level of the effluent BOD or the COD you like to maintain, you know? So let's say, so it depends on that. So let's say influent ma pretty much you can know what is coming in the effluent. सो डिपेन्डिङ अन द अब यसको कत्रो एरिएसन सिस्टम बनाउने भन्ने कुरा चाहिँ केमा डिपेन्ड गर्ने हो त डिपेन्ड्स अन दि वाट वुड बी दि डिजायर्ड एफ्लुएन्ट बिओडी कन्सन्ट्रेसन होइन सो डिपेन्डिङ अन यो डिजायर्ड एफ्लुएन्ट कन्सन्ट्रेसन वाट एफिसियन्सी इज रिक्वायर्ड होइन सो हामीले यहाँ मिनिमम एसआरटी कति चाहिन्छ त्यसको लागि सो आई थिङ्क वी अल्सो स दिस डायग्राम होइन एसआरटीलाई र हामीले चाहिँ एफिसियन्सीलाई प्लट गऱ्यौँ भने सो इट लुक्स लाइक दिस होइन सो यो एफिसियन्सी अफ दि बिओडी रिमुभल सो मेबी वी सेलेक्ट दि होइन समवेयर इन दिस जोन होइन सो तपाईँको एसआरटी चाहिँ सो सो अगेन विच क्यान बी अल्सो क्यालकुलेटेड युजिङ दि होइन हामीले चाहिँ यो क्यालकुलेट पनि गरे होइन सो 1/L इफिसियन्सी माइनस केडी भनेर सो अल्सो युजिङ दिस इक्वेसन यु क्यान क्यालकुलेट दि मिनिमम design SRD. So with the design SRD, you can take some safety factor and then you can calculate the design SRT. And design SRT ko value we can consider. So depending on your design SRT, then you can easily calculate the what would be your expected biomass concentration using the formula I think we discussed earlier. Okay. Okay, so अब के हुन्छ त एसआरटी कति लिने एसआरटी भन्दा one is you can calculate the minimum SRT. Let's say your first question should be what is your objective? Is your objective is only to remove the carbon or also your focus is also to remove the nitrogen. First, let's say if your focus is only to remove the carbonaceous removal, then you can see let's say our 3 to 5 days could be enough for the carbon removal. So if it's too short, के हुन्छ त तपाईँको एफएम रेसियो यु मेबी द बल्किनिङ प्रब्लम होला इफ इट्स टु लङ देन स्लज बिकम डिस्पर्स होइन सो यसलाई चाहिँ पिङ फ्लकुलेसन भनेर सो दिस मिन्स द्याट द स्लज पार्टिकल स्लजको फ्लक्स आर टु स्मल सो यसको सेटेलाबिलिटीको प्रब्लम कुड बी देयर होइन सो सो दि सेटलिङमा चाहिँ यसको प्रब्लम सो अप्टिमम सेटलिङ कुड बी होइन सो दि जोन सेटलिङ भेलोसिटी सो depending on this so your optimum let's say the velocity of the sludge can be calculated using the let's say optimum SRT can be calculated using predetermine the setting velocity also the range typical range operational range that's why it is somewhere between it also depends on the you can see that how the SBI values are affected by let's say different return slots ratio where different return slots ratio means that you can have a different SRT value so you can see that the MLSS concentration also can be maintained so the return it looks like the operational range somewhere between the 0.5 देखि 1 को बीचमा recirculation ratio seems to be good for the activated sludge system. Okay. Okay, let me now. So let's. So I think I think we mentioned that we'll start with the carbonaceous removal. So I would like to bring you to another lecture. So I hope you have gone through the PDF which was provided. Okay. So let's see. Let's hear if there's any questions so far. Okay, it's not then. So I would like to start the carbonaceous removal. I think I covered the basics of the activated sludge. Maybe repeated. Maybe I think a few things are covered in the undergraduate course as well. But I would like to. I think I covered the basics of the activated sludge in the earlier slide. So now the focus is on the carbonaceous removal, right? So I think we discussed some of the terminologies and then the relationship between the HRT, SRT, and what is SRT. And we discuss all these points. So if there's a system with solid liquid separation, your SRT is much more higher than the SRT. So in a steady state, so why we are doing the steady state? Our steady state भनेको के हो त 24 घण्टाको एभरेज कन्डिसनलाई कन्सिडर गरेर we are doing the design. So we are not considering the dynamic hourly flow को कुराहरु हामीले. So we are considering the Q average flow, Q daily average flow को चाहिँ हामीले पुरा गरेर we are doing the design होइन. सो भनेपछि एभरेज बिओडी कन्डिसन, एभरेज सिओडी कन्डिसन इन अ डे कति हो त? So total COD total that is coming in the, what is the average COD coming in the wastewater in a day, right? So we are considering the design, we are thinking these parameters, right? So what are the influent COD? What is the influent? What is the inflow? Average inflow coming into the system. So what happens is that during like a system is designed for a particular temperature, right? So any biological system, or I think even a physical chemical systems, they are designed for a particular temperature. So likewise, other you activate slot system, other it affects. So especially the more effect is on the endogenous respiration rate. You can see that the more or less the yield coefficient, right? ब्याक्टेरियाको यिल्ड कोफिसियन्ट भनेको तपाईँको वेदर लेट्स से इन टर्म्स अफ सिओडी होइन, तपाईँको चाहिँ मिलिग्राम अफ सिओडी पर मिलिग्राम अफ सिओडी यिल्ड or milligram of VSS or milligram of VSS per milligram of COD, it's more or less constant. So as the endogenous residue fraction, let's say you have a ml VSS र यसमा एक्टिभ ब्याक्टेरिया र ब्याक्टेरियाको डिके भएको रेसिड्यूको फ्र्याक्सन is also more or less constant. So this is not a temperature dependent. So only thing which is dependent on the temperature is the decay or the respiration rate. So when you have a decreased temperature, your respiration rate or the indigenous decay is also decreased. So this means that your sludge production is slightly increased. Sludge production is slightly increased. Also your aeration, carbonaceous oxygen requirement is also slightly decreased. So these are the effect, but this significantly the effect is very less. I think the effect is like even less than 1%. But though we must calculate the endogenous respiration rate for different temperatures. So this is given as let's say ordinary हेऱ्यो त हामीले अब अगाडिको डिजाइन इक्वेसनमा केडी भनेको थियौँ, but in this book it is denoted as B, है. So don't be confused होइन. सो हामीले यसलाई केडीलाई बी भनेर यहाँ रिप्रेजेन्ट गऱ्यौँ. अझ बी पनि ओर्डिनरी, अब यहाँ कार्बोनेसियस हामीले चाहिँ कार्बन रिमुभलको कुरा गर्ने भएको हुनाले हामीले ओर्डिनरी हेटेरोट्रपिक अर्गानिजम्सको मात्र यहाँ हामीले कुरा गर्छौँ. सो बिओएचओज भने कति हो त? सो द्याट दि एट अ पर्टिकुलर टेम्परेचरमा चाहिँ दिस क्यान बी क्यालकुलेटेड युजिङ this relationship. So endogenous respiration rate at 20 degrees Celsius. So theta C is the constant, for a particular temperature. So that theta to the power T minus 20. I think we talked about this theta value. I think during the BOD I think we talked about this. So also the experimentally these values are determined as 1.029, and also the standard value of let's say the OHO for 20 degrees Celsius is calculated at 0.24 per day. Calculate. So taking this as a reference, so you can use this equation and you can calculate the theta B OHO for any temperature T. Right? Temperature T it can be calculated using this relationship. Yeah. Okay, so it's all about the calculating this, doing the sizing of the reactor is all about. So what is important is we need to calculate what is the carbonaceous oxygen demand, right? So अब कार्बोनेसियस अक्सिजन डिमान्ड कति हो, स्लजको चाहिँ प्रोडक्सन कति हुन्छ रियाक्टरमा, त्यसै गरी स्लजको भोल्युम कति, तपाईँको रियाक्टरको भोल्युम कति चाहिन्छ in order to keep the let's say the concentration, particular concentration slotको चाहिँ गर्नको लागि कति चाहिन्छ भनेर. So this can be calculated using a by doing the steady state mass balance, हैन, using the kinetic equations we derive earlier. हैन, हामीले केही sludge production का इक्वेसन, अक्सिजन रिक्वायरमेन्ट का इक्वेसन, त्यसै गरी बायोमासको कन्सन्ट्रेसन का इक्वेसन, त्यही इक्वेसन युज गरेर we what we do in the next couple of slides is we try to make a mass balance of the COD and how they are transformed. हामीले के भनेको थियौँ त, सिओडीमा चाहिँ यदि सोलुबल फ्र्याक्सन सिओडीको अनबायोडिग्रेडेबल सोलुबल फ्र्याक्सन रिमेन्स अनचेन्ज, हैन. So others are transformed, you know. So it remains unchanged. Other like other COD, unbiodegradable COD particulate form, they become they become enmeshed with the sludge. Basically, biodegradable particulate COD, they convert into biomass. Basically, soluble COD, biodegradable COD. This again become the biomass. So we keeping this in mind. So now we are going to write some equations for the mass balance for the COD balance चाहिँ हामीले बनाउँछौँ है. सो अब टोटल सिओडीको फ्लक्स चाहिँ ट्रिटमेन्ट प्लान्टमा कति आइरहेछ त. सो द सिओडी फ्लक्स भनेको के हो त, मास इन्फ्लो. सिओडीको मास इन्फ्लो कति भइरहेको छ त, टोटल कन्सन्ट्रेसन सरी टोटल फ्लो रेट मल्टिप्लाइड बाई दि टोटल सिओडी इन दि इन्फ्लुएन्ट है चाहिँ. अब यो इन्फ्लुएन्टको टोटल सिओडी भनेको अब यसमा बायोडिग्रेडेबल अनबायोडिग्रेडेबल सबै कुराहरू हुने भयो. अब हामीले बिकज वी आर मच मोर इम्पोर्टेन्ट इन नोइङ दि लेट्स से what is the fraction of the COD that is converting into the biomass. भनेपछि अब बायोमासमा कन्भर्ट हुने फ्र्याक्सन भन्दाखेरि बायोडिग्रेडेबल फ्र्याक्सन. सो दि फ्लक्स अफ दि सिओडी विच इज बायोडिग्रेडेबल इन दि इन्फ्लुएन्ट. सो यहाँ एफसिओडी बिआई भनेको के हो त, बायोडिग्रेडेबल फ्र्याक्सन अफ सिओडी इन दि इन्फ्लुएन्ट. Sorry for that. So biodegradable fraction of COD in the influent is FCOD BI, right? So that is equals to the Q inflow multiplied by the CBOD. Biodegradable कति होता है, biodegradable COD भनेको कति होता, टोटल फ्र्याक्सन COD को टोटल माइनस द फ्र्याक्सन अफ COD सरी COD को टोटल. अब यसलाई फ्र्याक्सन, अब हामीले बायोडिग्रेडेबल COD भने टोटल फ्र्याक्सन 1 हुने भयो भने अब एफएसयु भनेको के हो त, एफएसयु भनेको तपाईँको कुन चाहिँ फ्र्याक्सन अफ COD द्याट इज अनबायोडिग्रेडेबल हैन, माइनस दि फ्र्याक्सन अफ सोलुबल COD द्याट इज अनबायोडिग्रेडेबल. एफएसयु भनेको फ्र्याक्सन अफ सोलुबल COD द्याट इज अनबायोडिग्रेडेबल. त्यसरी फ्र्याक्सन अफ COD द्याट इज अनबायोडिग्रेडेबल एन्ड इन दि पार्टिकुलेट फ्र्याक्सन. सो यसबाट हामीले 1 बाट घटायौँ भने, सो 1 इज द टोटल COD. सो यहाँबाट यसको वी गेट अ फ्र्याक्सन अफ दि, सो दिस इज ए फ्र्याक्सन अफ दि बायोडिग्रेडेबल COD. सो दिस इज नथिङ बट दि दिस इज ए BCOD हैन, BI हो यो भने चाहिँ बायोडिग्रेडेबल फ्र्याक्सन अफ इन्फ्लुएन्ट COD. सो COD टोटललाई हामीले के गर्यौँ त, अब Q मल्टिप्लाइड बाई COD टोटल मल्टिप्लाइड बाई द फ्र्याक्सन अफ दि बायोडिग्रेडेबल COD हैन. सो अब बायोडिग्रेडेबल यसलाई हामीले रिप्लेस गरौँ माथि. So the total flux of biodegradable COD can be represented as a flux of the COD multiplied by the fraction of the biodegradable COD. So total, let's say total, our total unbiodegradable inert fraction चाहिँ कति हो त है. So XU inert, so that is the XU total X U, that is the unbiodegradable fraction of the COD that is in the influent is equals to total inflow multiplied by the total particulate form मा भएको unbiodegradable COD को fraction multiplied by the total COD को fraction हैन. Then that is divided by the FUPO भनेको unbiodegradable particulate organic fraction. So that is the F is the fraction of the unbiodegradable particulate organic matter, okay? Fraction of the particulate organic matter. So this will give you the what, this will give you the Fx, so this will give you the Fx UV. so on biodegradable sorry unbiodegradable particulate को flux कति हो त है. so त्यसै गरी इनर्ट को चाहिँ फ्लक्स कति हो त. So inorganic fixed suspended solids को flux, unbiodegradable particulate organics को flux F यो भनेको this represented by the unbiodegradable particulate organics को flux भयो. त्यसैगरी inorganic fixed suspended solids को flux कति हो त. So that is Fx है, X FSS भनेको FSS भनेको के हो त. So this is the flux of the inorganic fixed suspended solids भनेको. अब यसमा के मेटल्सहरू होला हैन. So this is represented as milligram of inert suspended solids per day. So that is the flux of the. So first of all we need to make calculate the flux of different parameters like the flux of the organic COD, flux of the particulate organic, flux of the particulate unbiodegradable organic COD flux of the unbiodegradable inert or the inorganic or the fixed suspended solids. अब यो दुइटाले चाहिँ हामीलाई किन थाहा पाउनु त बायोडिग्रेडेबल मात्र भयो भने बायोमास कति हुन्छ भनेर थाहा हुन्छ यो दुईटा कुरा किन थाहा पाउनु परेको त दिस अल्सो बिकज दे आर अल्सो स्पेसली दिस वान है दे कन्ट्रिब्युट होइन मोस्टली इन दि स्लज प्रोडक्सन सो वी वान्ट टु नो what is the flux of the unbiodegradable particular organic matter है इन द इन्फ्लेक्ट अब यसको पनि सर्टेन फ्लक्स चाहिँ तपाईँको के हुन्छ त इट रिमुभ्स इन द प्राइमरी सेडिमेन्टेसन ट्याङ्क सो what is the mass of the अब यो चाहिँ इन्फ्लुएन्टमा भयो होइन सो दिस इज इन द इन्फ्लुएन्ट सो वाट इज द इनसाइड द रियाक्टर सिस्टम अब रियाक्टर सिस्टममा दुईवटा कुरा हुने हो रियाक्टर सिस्टममा यो सबै सिओडीहरू गएपछि के बन्छ त होइन इनसाइड द एरिएसन ट्याङ्क or the reactor होइन you have a biomass that is generally represented by X and you also have a substrate which is normally negligible because the most of the substrate in the effluent is already converted into the very negligible concentration of the effluent concentration of the substrate. And most of the COD are either the biomass is converted into the X, so maybe X could be TSS, X could be PSS, होइन सो अब रियाक्टरमा बायोमासको कन्सन्ट्रेसनको बायोमासको मास कति हो त द मास अफ बायोमास इन दि लेट्स से ordinary heterotrophic organism कति हो त the concentration of ordinary heterotrophic organism which is measured as the volatile solids multiplied by the working volume of the reactor. This will give you an idea about the X, the biomass concentration in the reactor. त्यसै गरी अब कति रेसिड्यू कति हो त अब यो त एक्टिभ ब्याक्टेरिया भयो होइन XOHO भनेको त एक्टिभ ब्याक्टेरिया भयो एक्टिभ ओर्डिनरी हेटेरोट्रोफिक अब त्यसै गरी रेसिड्यू इन्डोजिनस डिके भएर यी ब्याक्टेरिया OHO चाहिँ डिके भएर कति रेसिड्यू चाहिँ रियाक्टर सिस्टममा छ त भन्दा MXEOHO भनेपछि OHO को चाहिँ डिके भएर बाँकी रहेको रेसिड्यू होइन अगेन अब त्यो रेसिड्यू कन्सन्ट्रेसन कति हो त XEOHOV multiplied by the working volume of the reactor. त्यसै गरी कति अनबायोडिग्रेडेबल बायोमास छ त कति अनबायोडिग्रेडेबल बायोमास छ त कति अनबायोडिग्रेडेबल बायोमास छ त बायोमास चाहिँ तपाईँको यहाँ कति छ त X unbiodegradable organic biomass is XUV multiplied by so these all collectively this is the MLBSS sorry MLS this is the MLBSS अब यसमा तपाईँले अघिको XFSS फिक्स सस्पेन्डेड सोलिड जोडिदिनु भयो भने MLBSS मा के हुन्छ त दिस विल गिभ यु दि MLSS है सो दिस विल गिभ यु दि MLSS सो अब हामीले कसरी क्याल्कुलेट गर्ने त तपाईको X को कन्सन्ट्रेसन भन्दाखेरि अब कसरी क्याल्कुलेट गर्ने त अब कति बायोडिग्रेडेबल अब हाम्रो जति बायोडिग्रेडेबल BOD आइरहेको छ अहिले हामीले बायोडिग्रेडेबल BOD को फ्लक्स क्याल्कुलेट गर्यौं नि हैन अहिले बायोडिग्रेडेबल COD को फ्लक्स भनेको के हो त COD बायोडिग्रेडेबल I भनेर हामीले क्याल्कुलेट गरे हैन अब बायोडिग्रेडेबल COD अब कति कन्भर्ट हुन्छ त ML यसमा कन्भर्ट हुने ब्याक्टेरिया नयाँ ब्याक्टेरियामा कन्भर्ट हुने कति हो त यही बायोडिग्रेडेबल BOD नै कन्भर्ट हुन्छ तर कसरी कन्भर्ट हुन्छ त हामीले स्लज प्रोडक्सनको इक्वेसन क्याल्कुलेट गरे हैन स्लज प्रोडक्सनको इक्वेसनमा के थियो त कति BOD रिमुभ हुन्छ अथवा कति बायोडिग्रेडेबल BOD छ हैन ओस बायोडिग्रेडेबल फर्म अफ अर्ग्यानिक कम्पाउन्ड छ हैन त्यसलाई हामीले के गरे त सो युजिङ दिस इक्वेसन हैन using this equation you can calculate the total mass of the OHOs inside the reactor system. So just remember that this OHOs is the active bacteria inside the reactor. Right? So FBI like we also wrote it as FBI is equals to F COD total multiplied by 1 minus inorganic soluble को fraction COD को minus organic particulate को fraction. So this will give you the fraction of the biodegradable COD in the effluent. Right? So this multiply. I think you should know this equation. I think we calculated. We are just using the sludge production go formula here. सो दिस विल गिभ यु द अगेन अब नाउ कति कति रेसिड्यू कति बाँकी हुन्छ त त्यही गरी कन्सन्ट्रेसन वाट इज दि मास अफ दि टोटल मास अफ दि इन्डोजिनस डिके भएर बाँकी रहेको रेसिड्यू कति हो त टोटल एमएल टोटल ओएचओसको मासमा कति फ्रेक्सन चाहिँ यसको इनअर्ग्यानिक अथवा इनर्ट फ्रेक्सन छ अथवा डिकेको रेसिड्यूको फ्रेक्सन कति छ मल्टिप्लाइड बाई कतिको रेटमा चाहिँ डिके हुन्छ है द्याट मल्टिप्लाइड विथ दि टोटल मास अफ दि ओएचओस total mass of the OHOs in the system. So this will give you the, so now you can write the, modify the above equation as the, this form, FCOD. So this will give you the mass of the residues in the endogenous residue in the system. त्यसै गरी इनअर्ग्यानिक अर्ग्यानिक अनबायोडिग्रेडेबल फ्रेक्सन कति हो त त्यसको मास रिएक्टर सिस्टममा भन्दा कति इनअर्ग्यानिक बायोमास कति इनअर्ग्यानिक पार्टिकुलेट म्याटर अथवा सिओडी आइरहेको छ है त्यसको फ्रेक्सन कति छ त है अर्ग्यानिकको फ्रेक्सन कति छ है मल्टिप्लाइड बाई दि एसआरटी सो दिस विल गिभ यु दि टोटल फ्लक्स अफ दि will give you the total flux of the or total mass of the inorganic organic particulate matter in the reactor. It's very about total VSS, total ml VSS भने हामीले के भन्यो this is the sum of the active bacteria ml VSS भनेको this is ml VSS भनेको this भनेको के हो त यो mx VSS भनेको के हो त mx VSS is nothing but the working volume of the reactor multiplied by the x ml VSS हो अब x VSS मा के कुराहरु हुँदो रहेछ त यसमा एक्टिभ ब्याक्टेरिया एक्टिभ OHO प्लस त्यसको रेसिड्यू मरेको ब्याक्टेरियाको रेसिड्यू डिकेड रेसिड्यू एज वेल एज unbiodegradable organic particulate matter, so that is MXUV. So this will give you the ml, so ml VSS को total mass in the system, right? So okay, so finally, so simplifying the summarizing the above reaction and substituting, so you can calculate the mass of the VSS as the FCOD in the influent त्यसमा फ्रेक्सन कति छ हैन मल्टिप्लाइड बाइ दि प्लस कति चाहिँ इन्डोजिनस रेसिड्यू छ र कति इनअर्ग्यानिक अर्ग्यानिक पार्टिकुलेट फ्रेक्सनको फ्रेक्सन छ. So okay, so I think these are not new equations. We are already using the flux production को equation use गरेर, so we are just trying to calculate the mass flux र mass मात्र हामीले क्याल्कुलेट गरिरहेका छौँ है. This is nothing new. Okay, so अब किन थाहा पाउनु जरुरी छ? So we wanted to know, so what is the sludge production in the reactor, so what will be the expected MLSS, so what is the expected MLVSS or MLSS the system, right? So this is what we are trying to know. So अब यसको कम्प्लेक्सिटी अब यसलाई कतिको फ्र्याक्सनेसन पनि कतिको लेभलमा गर्ने भन्ने कुरा पनि again, so it depends on the objective. If your objective is also nitrification, so if your objective is also denitrification, so we are interested in influent readily biodegradable COD also. So if it's our intention is enhanced biological phosphorus removal, so we wanted to know what is the fermentable fraction of the COD, right? So it depends. For now, we are just for us. I think it is only important if you can know the total biodegradable fraction of the COD. कति हो त BOD को biodegradable BOD को fraction, right? So त्यो थाहा भयो भने I think it's more than sufficient to know or to calculate the TSS in the reactor, the oxygen demand, carbonaceous oxygen demand, and the sludge production rate can be calculated for the system, right? Okay. Okay, त्यसै गरी अब अघिको सिस्टममा we calculated the ML VSS. We only calculate the ML VSS. So now let's say if you are we are interested now to know the what is the total MLSS, right? Total MLSS ma अब के भयो त, what is the MLSS? So MLSS includes the MLBSS plus fixed suspended solids, होइन? फिक्स सस्पेन्डेड सोलिड्स भनेको अथवा फिक्स ओर इनर्ट सस्पेन्डेड आइएसएस. सो दि आइएसएसको कन्सन्ट्रेसन कति हो त, कति फिक्स सस्पेन्डेड सोलिड्स आइरहेको छ, सो त्यसको फ्लक्स होइन मल्टिप्लाइड बाई दि solid retention time will give you the mass of the mass of the inert suspended solids in the system. So once you know this mass, so now the total mass, let's say if you are interested in total ml, so total mass of TSS, then you can now calculate the mx VSS plus mx f mx fss. So this will give you the total suspended solids co system mass. So this is the same thing we calculated like the m. So let's say if the FSS भनेको इन्फ्लुएन्टमा इनर्ट सस्पेन्डेड सोलिड्सको कन्सन्ट्रेसन होइन. सो ओके, सो दिस इन्क्लुड्स दि समटाइम्स अब यो एफएसएसमा अब के पनि इन्क्लुड हुनसक्छ त भने त्यो डिके भएर ब्याक्टेरियाको लाइसिस हुन्छ. यो लाइसिस हुँदा पनि केही इनर्ट सस्पेन्ड हुन्छ, जसरी हाम्रो ब्याक्टेरियाको सेल CHONबाट मात्र नबनेर, सो इट मे अल्सो इन्क्लुड्स आइरन सिलिकन एक्सेट्रा होइन. यो पनि डिसइन्टिग्रेट भएर रिलिज हुन्छ. सो once the microorganisms are decay, so we also consider these release of this concentration in the fixed suspended solids होइन. सो एफएस भनेको के हो त, इनअर्ग्यानिक कन्टेन्ट कति हो त स्लजको होइन. लेट्स चाहिँ 1 मिलिग्राम स्लज OHOs को VSSमा 0.15 मिलिग्राम इनर्ट सस्पेन्डेड सोलिड्स हुनसक्छ. and this value can be increased. Let's say if you are using a EPBR process, enhanced phosphorus biological removal process, maybe this fraction could go quite high. And if it's only a conventional activated sludge where there is no sludge enhanced biological sludge removal, then this milligram of ISS up to 2 milligram of OHS ratio is quite different. Okay. And then now okay, so the total reactor MLSS, MLSS, so this is the MLTSS is the के भयो त, यो त MX VSS plus MX FSS होइन, fixed suspended solid. So total what is the ratio of VSS to TSS? I think I started with saying that maybe this value can vary between the होइन, this value can vary between 0.6. I think this is quite low. Normally it is somewhere between 0.8 को चाहिँ आसपासमा हुन्छ, or maybe sometimes 0.85 लिने चलाउँछ. So this value can change. Let's say if it's a sludge accumulating, phosphorus accumulating, this value will decrease. And while if it's in the activated sludge process, maybe so this value is normal between 0.8. So the ML is ratio. So BT is the ratio of VSS to TSS. So it's estimated ratio. So this is a FBT is the ratio between the VSS to TSS. Right? So what is the carbonaceous oxygen demand? So what is the oxygen demand? I think if you remember, like we wrote the oxygen demand equation RO2 as कसरी लेखेका थियौं त, कति oxygen remove भयो हैन, कति BOD remove भयो हैन, multiplied so by Q हैन minus 1.42 px, if you remember, right? We did this. What is sludge production भएको थियो त 1.42 times px, so Q multiplied by कति BOD remove, or this is also a COD को biodegradable influent को fraction हैन. So again now we replace the flux of the COD influent. I think we calculated above in the influent को flux calculate गर्दा. So the total oxygen demand now is here कति त, so your oxygen demand is, so कति इन्डोजिनसमा चाहिँ युज हुन्छ है. सो व्हाट फ्र्याक्सन इज युज इन द अक्सिजन डिमान्ड इज कति इन्डोजिनसमा चाहिँ युज हुन्छ, कति यिल्ड माइक्रो अर्गानिजम यिल्ड प्लस इन्डोजिनस हैन 1 माइनस द इन्डोजिनस को चाहिँ रेस्पिरेसन रेट र व्हाट इज द फ्र्याक्सन अफ द इन्डोजिनस रेसिड्यू इन द टोटल OHOs हैन. So this multiplied by the yield. If you remember, This is the sludge production को equation. Hey, okay. So if you replace the biodegradable influent को fraction like, so in the earlier equations we determine, then this will give you the total carbonaceous oxygen demand. So total carbonaceous oxygen demand reactor. So if you just want to remove the BOD, so your total oxygen requirement can be calculated using this equation. Right? So FOC is the carbonaceous oxygen demand, milligram of oxygen per required per day, or the kg of oxygen required per day. And that is the carbonaceous oxygen demand. Let's say if you want to determine the volumetric oxygen demand, then you multiply it by the, sorry, if you divide, you need to divide it by the total working volume of the reactor, will give the volumetric oxygen requirement, right? Okay, so अब यहाँ यसो हेर्दाखेरि, so what is the भनौँ त, let's looking at the equation here. So तपाईँलाई, if you are interested, let's say, to know the concentration of the biomass, so what is the important factor? So यहाँ हेर्नुभयो भने, so SRT, hey, SRT, the only changing factor is the SRT. So this, at the different temperature, your FXEO remains constant. B also, it is also dependent of temperature, right? 10 डिग्रीमा गर्नुहुन्छ, 20 डिग्रीमा गर्नुहुन्छ. So let's say the only variable parameter here is your SRT. So when you change your SRT, your slot production also changes. तपाईँको हेर्नु त सबै कुरा चेन्ज हुँदो रहेछ. एक्टिभ अर्गानिजमको चाहिँ कन्सन्ट्रेसन पनि, मास पनि चेन्ज हुँदो रहेछ. रेसिड्यू, त्यसले बनाउने रेसिड्यू पनि चेन्ज हुँदो रहेछ, होइन? तपाईँको चाहिँ इनर्ट अर्ग्यानिक फ्रेक्सनको मास पनि चेन्ज हुँदो रहेछ विथ द चेन्ज इन दि एसआरटी, होइन? So what I want to, I think at the end of this lecture I will give you some one assignment. So you see that during the changing the different SRT, what will be the change in the sludge production, what will be the change in the let's say the carbonaceous oxygen demand, because you see that with the change in SRT value, your carbonaceous oxygen demand is also changes, होइन? So अब रह्यो कुरा अक्सिजन डिमान्डको कुरा हामीले निकाल्यौँ. वी अल्सो क्यालकुलेटेड रियाक्टरको चाहिँ टोटल मास अफ द स्लज, होइन? डिफ्रेन्ट खालको स्लजको क्वान्टिटी हामीले क्यालकुलेट गर्न, मास क्यालकुलेट गर्न सक्यौँ युजिङ दि फ्लक्स अफ दि सिओडी, डिफ्रेन्ट फ्लक्सको चाहिँ फ्रेक्सन्सबाट, सिओडीको फ्रेक्सन्सबाट, स्पेसली बायोडिग्रेडेबल फ्रेक्सनबाट वी क्यान क्यालकुलेट दि the mass of the biomass inside the reactor, right? Sludge production say per day we can calculate. So how to calculate the working volume, होइन? रियाक्टरको वर्किङ भोल्युम कसरी क्यालकुलेट गर्ने त? सो okay, so the reactor को working volume चाहिँ calculate गर्नको लागि, it's one thing is, first of all we need to determine the at what SRT we like to calculate. So at what SRT, or what is the ranges of the SRT we like to operate the reactor, in which we would like to operate our reactor. Two कुरा चाहिँ we need to determine, and also we need to determine the what is the expected MLSS concentration we like to operate. So again, going back to the slide, if you just remember, like, there were different technologies, and extended aeration system थियो, conventional activated sludge system थियो, there was a completely mixed system was there. So different system, they have a different concentration of the XTSS. So which sort of system you like to operate? So it depends on the designer's discretion, होइन? तपाईँले कस्तो खालको सिस्टम डिजाइन गर्नु खोज्दै हुनुहुन्छ. So you select the so you select the XTSS, right? So we can calculate using the COD को loading rate बाट. What we can do is we can calculate the MXTSS हो. हामी कसरी MXTSS क्यालकुलेट गर्न सकिन्छ? युजिङ द COD को इन्फ्लक्सबाट. COD को इन्फ्लक्सबाट काइनेटिक अहिलेको चाहिँ अगाडि हामीले मेन्सन गरेको इक्वेसनबाट. So you can calculate this using the COD influx, COD fractionation. So now if you divide it by the let's say XTSS, you can calculate the working volume of the reactor, for which you like to keep this X TSS concentration. So 2000, 3000, कति मेन्टेन, कस्तो सिस्टम डिजाइन गर्दै हुनुहुन्छ? एक्सटेन्डेड एरिएसन, conventional activated sludge, or completely mixed system. So depending on that, you select the XTSS and you calculate the reactor volume, right? So okay, I think I'm going to stop it here. I think it's been almost 1.5 hours. Okay, so the I think the assignment part. So what you need to do is, okay, I haven't showed you the yet the values. So there is one a design example given here. Right? So the design example is given here. So based on the equations we described earlier, हामीले यहाँ के गरेको छौँ त सो यहाँ अब हामीलाई भोल्युम क्यालकुलेट गर्नको लागि सम सम डिजाइन प्यारामिटर्स आर गिभन हियर है अब यो डिजाइन प्यारामिटर्सहरूमा के दिएको छ त तपाईँलाई फ्लो रेट दिएको छ है दि एज वेल एज दि डिफ्रेन्ट सिओडीको फ्रेक्सनेसन सो वाट वी आर डु इज वी युज दिस बोथ सेटल प्राइमेरी सेडिमेन्टेसन गरेको र नगरेको दुइटै वेस्ट वाटरलाई हामीले लिन्छौँ. So what we do is we calculate the we see that let's say these parameters are given for a particular temperature. Right? So particular temperature को लागि यो दिएको छ. So I will fix one let's say the design temperature. Let's say we do it for both 14 degrees को लागि पनि 22 degrees को लागि पनि. So for both 22s and for 14 degree we calculate the endogenous OHO को चाहिँ endogenous हामीले क्यालकुलेट गर्छौँ. सो वी नो दिस क्यान बी क्यालकुलेट युजिङ दि स्ट्यान्डर्ड 20 डिग्रीको टेम्परेचर थिटा होइन टु दि पावर टी माइनस 20. सो यहाँबाट यो इक्वेसन युज गरेर वी क्यालकुलेट दि endogenous decay. So using this endogenous decay factor, so what you need to calculate is you need to calculate the mass of TSS. So the reactor system aeration tank ma what is the mass of total mass of TSS and what is the oxygen demand, right? What is the active fraction of the bacteria, right? So total active fraction OH को कति हो र TSS चाहिँ कति वेस्टेज गर्नुपर्ने. सो ड्युरिङ द चेन्जिङ सो लेट्स से यु टेक दि एसआरटी 3देखि 30 दिनको एसआरटी लिएर सो what you need to do is you need to prepare an excel sheet calculation excel sheet होइन. So where you calculate the different the mass balance है यो अघि हामीले क्यालकुलेट गरेको. So here's one example given. So I will also talk to this example maybe on Tuesday. So one thing I would like you to do is try to calculate, come up with a calculation. I'll show you one example. Okay. So what you need to do is okay. So just a moment. Okay. So what I would like you to do is so for both raw and the settled condition. So both for the raw and settled condition, so you need to calculate ML, MXTSS, XVSS, as well as you need to calculate the let's say for both 14 degrees and 22 degrees Celsius, you need to calculate the oxygen. I think you just need to plug the equations, right? These equations. I think we discussed earlier, right? So depending on the given condition, you are given the conditions. Let's say the daily COD को फ्लक्स कति आइरहेछ र र सेटलमा कति हो त्यसको चाहिँ अनबायोडिग्रेडेबलको फ्र्याक्सन कति आइरहेको छ त्यहाँबाट तपाईँले बायोडिग्रेडेबलको फ्र्याक्सन क्यालकुलेट गर्न सक्नुहुन्छ. एन्ड युजिङ द डिफ्रेन्ट एफसिबी भ्यालुज गिभन इन दि एफ्लुएन्ट है कन्डिसन यु निड टु what you need to do is you need to calculate it for different let's say different एसआरटी को भ्यालुजको लागि कार्बन एक्सेस डिमान्ड कसरी चेन्ज हुन्छ तपाईँको त्यसको चाहिँ एमएक्सटिएसएस कसरी चेन्ज हुन्छ एमएक्स भिएसएस कसरी चेन्ज हुन्छ है. So this is what you need to calculate, and I think you need to come up with a different, let's say, some sort of this sort of graphs, right? Okay, so mass reactor. So when you change the SRT from 3 to 30 days, so how your MXTSS, MXVSS, MXTSS, right, is going to change for both 14 degrees and 22 degrees Celsius. Right? Also the active fraction, right, FA B को fraction कसरी चेन्ज हुन्छ त्यसै गरी तपाईँको चाहिँ वेस्ट स्लज है वेस्ट स्लजको क्वान्टिटी कसरी चेन्ज हुन्छ त्यसै गरी है what is the quantity of the waste sludge भनेको sludge production daily sludge production you just need to calculate the daily sludge production right? So that is the total चाहिँ MXTSS per day क्यालकुलेट गर्ने हो. त्यसै गरी तपाईँको अक्सिजन रिक्वायरमेन्ट FSOC है. सो हाउ इट चेन्जेस होइन फर बोथ र को लागि र सेटलको लागि फर बोथ 14 degrees and the so you can see that the यहाँ हेर्नुभयो भने 14 डिग्री सेटल र होइन रको लागि कसरी चेन्ज हुन्छ टेम्परेचरको इफेक्ट है क्यान सी द्याट दि इफेक्ट अफ द टेम्परेचर होइन तपाईँको चाहिँ फर सेटल स्लजको लागि र उसको लागि है सो आई थिङ्क दिस इज वाट यु निड टु डु सो आई विल गिभ यु दिस पोस्ट दिस असाइनमेन्ट बट वाट यु निड टु डु इज ओके यु निड टु चेन्ज दि एसआरटीको भ्यालु र त्यसमा मास ब्यालेन्स कसरी चेन्ज हुन्छ हाम्रो है एसआरटीको भ्यालु चेन्ज हुँदाखेरि किपिङ दि इन्फ्लुएन्ट सिओडीको फ्लक्स प्यारामिटर एट सेम सो द ओन्ली यु चेन्ज दि एसआरटीको भ्यालु होइन इन दोज द इक्वेसन्स वी डिस्कस अर्लियर okay, so we'll do one example in the class. I think on Tuesday, 10 to 12, 10 to 11, and then you'll be doing it on your own. है त त्यसबाट हामीले कसरी हामीले भोल्युम क्याल्कुलेट गर्छौँ also we'll do one exercise on that. So for now, I think I'm going to end it here. So okay, if there's any questions so far. इट लुक्स अ बिट कम्प्लिकेटेड तर अघि मैले जुन धेरै त्यो टर्मिनोलोजिसहरू आयो धेरै प्यारामिटर्सहरू आयो दिज आर जस्ट दि नोटेसन्स है अब कति त्यो इनअर्ग्यानिक इनर्टको फ्रेक्सन्सको नोटेसन्सहरू छ यु जस्ट निड टु नो दिज यसमा केही त्यो सोफिस्टिकेटेड इक्वेसन्सहरू होइन इज जस्ट अ मास ब्यालेन्स है फ्लक्स मात्र क्यालकुलेट गरे हो मास फ्लो रेट मात्र हामीले क्यालकुलेट गरे हो है त्यसको कन्भर्जन कसरी हुन्छ भन्ने कुरा हामीले त्यो डिजाइन इक्वेसन एक्टिभेटेड स्लजको स्लज प्रोडक्सनको इक्वेसन है हामीले एरिएसनको चाहिँ एरिएसनको रिक्वायरमेन्टको इक्वेसन सो इट केम फ्रम देयर है सो देयर इज नो डिफ्रेन्ट इक्वेसन्स जस्ट वी आर जस्ट मेकिङ दि सिओडीको मास ब्यालेन्स मात्र हामीले बनाइराखेको हो सो ओके आई विल सी यु अगेन आई डोन्ट वान्ट टु कभर मच है आई थिङ्क विल डु द्याट फिजिकली सो आई विल सी यु अगेन अन ट्युजडे 10 देखि 11 है त So I think until then, I'm going to end it here. If you have any questions, I think we'll still have some time to discuss. Okay.
Thank you, sir.
Okay. Thank you then. Bye.
Yeah, no, okay, sir.